Okay, final section of our series of videos on the chain rule. Let's go ahead and jump right in. Let's say I have g of t is equal to the square root of 1 over t squared minus 2. Okay. Now, that is a quotient inside of a radical. Now, I've already told you that radical functions are power functions in disguise. I've told you that reciprocal functions are power functions in disguise. This is just a reciprocal radical function, okay? And actually, it might be easier to actually see it like this, which is completely legitimate, before we actually turn it into that, okay? This looks intimidating. This does not. Okay? So like I said before, stop, think, then do. Okay? And so we have g prime of t. Now that's stuff to the negative 1/2. So it becomes negative 1/2 stuff to the negative 3/2 times the derivative of stuff. Okay? The stuff just happens to be 2 squared minus 2 times, and the derivative of that, of course, is 2t. If you were asked to simplify it, the 1/2 and the 2 cancel each other out. You get negative t over t squared minus 2 to the 3/2 down here in the denominator because it had a negative right there. Ta-da! There you go. Okay? Now, let's do one that's maybe a little bit more difficult. Let's see. F of x is equal to... Okay. And of course, this is what's known as nested radicals. And of course, the first thing I'm going to want to do is I'm going to want to turn all of this into exponents. That is the very first thing that I want to do here. Okay? Now, that is obviously, 2 layers, or actually 3 layers, but the inner layer isn't really going to matter because you see the fact that that inner layer is x plus 1, a linear whose derivative is 1. So that's kind of a non-issue. So we have f prime of x. That's stuff to the 1/2, and therefore it's 1/2 stuff to the negative 1/2 times the derivative of whatever's inside those brackets, which just happens the derivative of that term is going to be 0, so we really only have to worry about this one right here. 1/2 x plus 1 to the negative 1/2, okay? And of course that simplifies rather easily. Nothing but a 1 goes in the numerator, and we have 4 x plus 1 plus 1 and then x plus 1, right? Because that whole thing to the negative 1/2, that's here, and then just the smaller to the negative 1/2, and there we go. Okay. Now let's do a tangent line problem. So let's say we have g of x is equal to x minus 2 plus rad x plus 3, and I want the equation of the tangent line at 6, 5. Okay? Now, of course, I set it up like this so I could have a nice integer. Order pair. This doesn't really wind up being all that difficult. It's kind of chain rule-ish, only in name, because like I said in the last example, the derivative of the inside winds up being 1, but it's a decent problem to go ahead and work on anyway. This one winds up being 1/2 x minus 2 to the negative 1/2 plus 1/2 x plus 3 to the negative 1/2, or 1 over 2 rad x minus 2 plus 1 over 2 rad x plus 3. You could put that into a single expression, but why in the world would you ever want to? All you need now is to go ahead and evaluate that function at 6. You know that when you plug 6 into rad x minus 2, you're going to get rad 4, or 2. So that's going to be 1/4. And then, of course, when you plug it into here, you're going to get 1/6. 1/4 plus 1/6, obviously they have a common denominator, a least common multiple of 12. So that's 3/12 and 2/12, so 5/12. There's your slope. There's your point, okay? And so y minus 5 is equal to 5/12 x minus 6. That is point slope, your equation of your tangent line, okay? Now, another chain rule problem. Let's go back to trig. We haven't done a trig one in just a little while. We have 3 secant squared pi t minus, let's go ahead and turn that into a t right there. Pi t minus 1. X, t, whatever, doesn't really matter. Now, what is the outside-most thing going on here? Now, the 3 is just a coefficient. It just comes along for the ride. Now, if I want to take this and actually take it out of lazy man's notation, it looks like that, okay? Now, the biggest thing going on is, of course, the squaring. Then the secanting, if we can call it that, and then the linear inside. So it's a 3-layer one, and I have f prime of t. We need to go ahead and put the 3 right here because it comes along for the ride, and then I need to start differentiating. It becomes 2 secant pi t minus 1. Now I could go ahead and put brackets around this and say it's to the first, but it doesn't really matter, right? Because when you take it from the second power to the first power doesn't really need to be stated. But we'll go ahead and put it right there just for emphasis. Now, I know that the next layer is secant stuff. Well, the derivative of secant stuff is secant stuff tangent stuff. Now, like I said in the last one, the last chain rule problem, the mistake that I see with secant, or with cosecant for that matter, is the fact that people fail to put the angle measurement for secant. It's like they put secant tangent pi t minus 1. As if secant doesn't require the angle measurement expression, which, by the way, it does, okay? So be sure that you put an angle measurement expression for both of the trig functions, okay? And then, of course, we need to take the derivative of the inside. The inside here is, of course, the linear, and the derivative of any linear is just its slope. So this winds up being 6 pi secant squared pi t minus 1 times tangent pi t minus 1. That would be it simplified, and that is your derivative. Okay? Now, we're probably going to get done, and this one's probably going to be just a little bit shorter because I only really have one more example that I want to do for you. I feel it necessary to do at least one more exponential. And this one's just a little bit nasty, but, that's where we have fun. I always remember Roe used to just groan when I said, "Ooh, that's a fun one." So, "Ooh, that's a fun one," and you can groan all on your own at home. Okay. What is the outermost thing going on? Well, to the 4th power is the outermost thing going on. So that's stuff to the 4th, okay? And then each independent term inside the stuff has a chain rule with respect to its exponential, okay? So let's first of all do the outermost. So that's 4. So the derivative of stuff to the 4th is 4 stuff cubed. Now we need to take the derivative of each term. And each term winds up being 2e to the stuff times the derivative of stuff. And on the second one, it winds up being 3e to the stuff times the derivative of stuff. Okay? Now, that winds up being 4 2e to the 3x plus 3e to the negative 2x. And you could probably factor out a 6 right here because, you know, the numerical factors of this term are going to be 6. The numerical factors of this term are going to be negative 6. So you can multiply by 6 e to the 3x minus e to the negative 2x. And then, of course, your next one would just be 24. Oops, forgot to bring the cube down. Very, very important to bring the cube down. 2e to the 3x plus 3e to the negative 2x cubed times e to the 3x minus e to the negative 2x. And that, of course, would be it simplified. Okay, so like I said, the whole idea of chain rule is the taking of derivatives of composite functions. And you need to figure out what is happening at each layer. What is happening in the outermost, what is happening in the innermost, and what's happening in between. Of course, the only guide that you have in terms of that is your knowledge of order of operations, and you need to go ahead and remind yourself of all of those little things if need be. But guys, that's the chain rule. This is the last section of stuff that would be review for you. When we start on 3.5 and moving forward, this is the last piece of differentiation material that you've actually seen before. As we move forward, we may have to expand the number of videos that I supply for you because it will be new material. But I think that's something to look forward to because there's lots of neat stuff that comes along after this. I hope it's been helpful, guys. Like I always say, if you have a question, please do email me, and I'll either post a video, respond by email, or of course we can cover it on the Saturday Skype session. Please do keep in contact with me in terms of telling me what y'all need. That way I can better tailor the things that I'm doing for you. I hope everything's going well, and I will talk to y'all soon. Bye.